everyone. Thank you for coming. I'm David Woods. I've been contributing to Cython for about 6 years or so, something like that. So a reasonable amount of time. So I want to talk to you about how to write parallel programs with it, what features we have that will help you, and that kind of thing. And so the outline, just very quickly, I'm going to go through a bit of introduction. Then I'm going to have a look at sort of 3 different how-tos, the p-range feature that's built into it, just using Python stuff and the subinterpreter stuff that's being added to Python. Then I'm going to move on to what's new, and what's new is mostly with respect to the free threading world and treating that a bit better, and then just some sort of final slides to sum up. You know, if you've got a Cython module, what should you be doing, that kind of thing. So, I mean, the motivation behind this talk is parallelism has been available in Cython for a long time, and some of you may hopefully have used it, and some of you may not. But until recently, parallelism in Python as a whole has been limited by the GIL, as most of you know. Cython was a little better because we actually let you release it and do a bunch of stuff without it. But the recent developments in Python as a whole has been free-threaded Python and the addition of subinterpreters, both of which provide you with sort of new mechanisms to attack parallelism. So the motivation of this talk is that we've been doing a lot of work, mainly for free threading, and to present some of that. Before we go too much further, I just want to cover what is Cython itself, just so if you're in the wrong room, you can kind of realize this now and leave or whatever. But the basic idea is it compiles Python-like code, so not quite Python syntax, but pretty close to C or C++. So it's a way of accelerating Python, so it can make fast modules that, you know, that run a sort of mixture of C code and Python code. And that's especially for loops and arrays, because loops are traditionally really slow in Python, and, you know, if you work with NumPy, you never write loops and you try to vectorize it. And in Cython, you can write loops, and that's actually quite good. And the other thing it can do is it can be a binding layer for C and C++ libraries, so it can let you call some external library you want to use. And so the sort of analogy I like to use is that sort of normal binding layers have this quite strict, like Python and compiled code interface, you know, where there's a barrier you've got to cross, and that barrier is a bit heavy. And Cython kind of lets you blur that layer and put it where you want it, and keep writing Python code quite low down, you know, if that's what you're comfortable with. So hopefully that makes sense. That's what we're talking about. Before we go too much further, obviously hopefully know about the global interpreter lock, this giant lock that kind of used to exist to protect the Python internals from corrupting itself. So it's mostly for the benefit of Python, not for the benefit of you. So it's just to make sure that the Python can work and doesn't mess up. The free-threaded build, which is currently still somewhat experimental, removes that. So the idea in the free-threaded build, instead of the global interpreter lock, you have an attached thread state, which more than one thread can hold. Because obviously Cython's quite an old project, it's like 20 years old now, everything in the documentation, in the commands you use, refers to the global interpreter lock. And because and I'm going to say global interpreter lock, but when I say global interpreter lock, what I really mean is attached thread state. So if you can sort of humor me and mentally make that substitution on my behalf, thank you. So, I mean, the other thing I wanted to talk about, there's quite a bit of discussion of thread safety, which can mean, I guess, a number of different things. So you're writing parallel code and you're interfacing with the data from multiple places, and this obviously means that you've got different threads can interfere with data that other threads are working on. So by thread safety, we're thinking about how can we make sure that we get a correct and consistent result. So the first example I've got is just this a plus equals 5. And in the comment, you can see there's actually two steps. There's a read a, there's an add 5, and there's a write a. And if another thread gets in there and writes something else to a in that gap, then you've got the wrong answer. you've got, the second example was like, if a container isn't empty, then pop a value from it. But if another thread pops a value in the gap between checking it's empty and popping the value, then it's going to go wrong. So again, that's potentially unsafe. And then there's a sort of implementation of pop, which I've written there. And again, the point is to implement pop, to pop from the end, you're reading the length of the container, you're reading the last element, then you're kind of truncating it. And there's multiple steps. And if another thread gets in the way, then it all goes wrong. And that's usually not what you want. So the important thing about these thread safety things is they're usually multi-step. So you read something and you do something with the data. And typically we want to make sure that you're doing the right thing and nothing else will change the data in between. So the obvious way we do this, which is on the the left-hand side, is we use locks. So we say with some lock, some lock ensures that only one thread can read the variable when you say plus equals 5. Similarly, you say with some lock, so you've locked something that owns a container. You can then check it's empty, and nothing else can get that lock while you pop it. Obviously, one of the questions here in the sort of gap there is it the same lock or a different lock? If it's the same lock, you've got the possibility of deadlock because you can't hold it twice. So even though it's the same thread, it may deadlock. So that's something to consider, which I'm not going to go into in too much detail. On the right-hand side, as you look at it, I just present a few other examples. So with this adding 5, the other thing you can do is you can use atomics, which are really a sort of a lower level language structure, but that's a number that's an atomic operation sort of happens in one go. So the plus equals 5 isn't actually broken down into 2 steps. It's literally just 1 step. Nothing can interrupt it. And the nice thing about that is you're not messing around with locks, so it's quick. But you can only do simple stuff with it. The container pop example, maybe instead of checking empty, you just have an interface which says, try to pop, but none is a valid answer. If there's nothing there, we'll return none, or some placeholder value. So again, that prevents you having to lock it. You don't have to do an empty check, but there's probably still an empty check and some locking internally. The final sort of thread safety example that I just wanted to get is this. So you've got read a temporary from some shared store and then add one to the temporary. The reason I mention that is because internally in the sort of implementation of Python, that happens all the time. You read a Python object and then you incref it. You say, I've got another reference count to it. And actually that's very hard to do in a thread safe way. And so they've done all these kind of silly, I say silly tricks, but clever and silly tricks, which about not deallocating memory particularly quickly, so you can get away with reading something that may have changed. So that's kind of a bit of internal thread safety in Python, which, if done wrong, means that you can end up messing up the interpreter, your reference counts being wrong. So I guess there's a number of outcomes for getting thread safety wrong. So it may just crash. So the Python interpreter, the attitude the Python interpreter takes is that they won't crash, but that's the thread safety you get. So that's what the three-threaded interpreter aims for. If you may well get the wrong, so even if it doesn't crash, you may get the wrong answer. And getting the wrong answer potentially, has more serious consequences than the interpreter crashing. Getting the wrong answer, could mean that something like industrial explodes and kills you all, which, wouldn't be good. Or it could mean that 2 things get printed in the wrong order, in which case, who really cares? But the thing we're aiming for is code that produces the right answer. So we're aiming to give you the tools to get to this sort of logically thread safe, where things not just don't crash, but they give you the answer that you want. But you can also make it kind of conditional. So you're totally fine to say, this class I'm writing can only be accessed from one thread. Only one thread can use my class at once. but my module as a whole will be thread safe. You know, people can do lots of independent calculations, but they shouldn't be playing with a sort of a single class for multiple threads. And that's a reasonable thing to do, and that's mainly enforced just by documentation. So yeah, if you want to impose that kind of condition, write it down, please. So now that's kind of the introduction bit largely over with. So let's have a look at how you can do parallelization. So in terms of Cython, most people think of p-range and parallel, largely because they're directives that are built into Cython. And so that's kind of what everyone uses, and that's what our documentation uses. And they end up being fairly thin wrappers around OpenMP, which is the C and Fortran way of writing parallel code. And my argument is that you may not actually want to use these. These are good for specific situations, but not a general solution. And I'm going to tell you about that on the next slide. So, well, not on the next slide. I'm just going to give you a quick example of how you use p-range. So I guess some of it is that you've got a magic directive. You C import p-range from Cython. And the two examples I've given are really just very trivial examples. They're just looping over arrays and summing things up in one dimension. So the first example is just in 1D. And then the second example on the right-hand side of the screen is in 2D. And they kind of both illustrate different things. The first example, you've got this total. So you initialize total to 0 and put it in a p-range loop. So that's just p-range is like range but parallel. And then you do a sum squared as you go. And that's what it's aiming to illustrate. And this gets magically transformed into an OpenMP reduction. So essentially, it doesn't matter that you're sort of doing the total equals total plus some value. OpenMP deals with this nonsense for you and makes sure it works. And then in the second example, the 2D array, I take a slightly different approach, and I essentially do it a row at a time. So you parallelize it by rows, but each thread only reads one row. So in this case, outview. The addition to outview right at the bottom isn't a reduction, but it works correctly because only one thread is sort of reading that row. And the other thing to mention before I move on is you do have to pass these extra compile and extra link arguments to tell the C compiler to use OpenMP. Otherwise, it will not really parallelize. And so I guess before I move on, these are examples of exactly where p-range should be used. You're doing something sort of simple over an array, you know, accessing one row at a time or that kind of thing. And what I'd really discover, if your problem is like this, then use it, and it's a great tool. And if your problem isn't like this, then don't try to force it into it, if that makes sense. You know, don't try to do sort of tricky stuff and add synchronization within these p-range loops. It either works nicely or it doesn't. The sort of limitations are that in the documentation we say that OpenMP doesn't always play nice with other threads. While preparing this talk, I tried to make it break, and it seemed to work on my computer, so I can't actually prove that it doesn't. But be slightly wary if you're mixing it with other threading systems, then OpenMP may not play nice. It only fits into specific problems, as I've said, and there's limited control of how data is shared between threads. So unfortunately, there's a bunch of opaque rules. And the idea of this slide is not that you remember the opaque rules. The idea of this slide is that you know there's a bunch of opaque rules and sort of stay away from anything that might touch it. So that C-types aren't shared between threads. So each thread will have an individual copy of CVAR. PyVAR, each thread will not have an individual copy, and there'll be a global copy. Writing to a C array, because it's indexed, that isn't shared, so they all have the same C array, and the preset is shared because you don't write to it. So there's all these opaque rules that you know, we're sort of in there historically, but make it a little hard to reason about. So this is kind of why I'm saying don't necessarily go there as your first choice. What I would recommend, if you can possibly do it, is that in general, Python code is valid Cython code. And so Cython functions are just regular Python callables. So you can just use all your Python threading tools that you know and hopefully love and are familiar and are a bit higher level. I recommend minimizing the data sharing between threads, and we've got an example sort of next time. And so you don't actually need any special Cython magic. You just from threading import thread, and it works. So here's an example. So the example I've kind of come up with as a quick illustrative example is that we're reading from a list of files, and we're putting words in a set. So you get a list of unique words at the end of this. And the bad example is which I'm recommending you not doing, is that you've got one set which is shared between all threads, and as you go through each word, you call add on that set. So you've got multiple threads writing to the same place. This relies on set add working in a thread-safe way, which it does, but I don't know if it's documented. And it doesn't perform particularly well. So, like my better example is, at the cost of a bit more work, each thread has its own set. So each thread builds its own set of words, and then right at the end you combine them. So you call sort of update on the overall result at the end. So I mean that generates a bit more work when you kind of read it, because it moves some of the work out of your threading, but it performs a lot better. And so I mean we've got some timings here just to sort of illustrate the point. So the main point is that the bad example, when you try to parallelize the bad example, it actually gets a lot worse, both in the free threading build and in the regular non-free threading build. So don't do that. That even in the free threading build, you're generating a lot of locking, and it's worse than just not parallelizing it, because each time it adds something to the set, it sees as a bit of contention and locks. The good example works better. Cython is only 10% faster, but that's kind of not really to illustrate the point. The good example doesn't perform too well on the non-free threading build on the right-hand side of the screen, but on the free threading build, you've got a factor of 2 speed up, which you may be fairly happy with. The other thing you can do in Cython, and the intention is please don't read this code. It's a giant screen of code that's just supposed to illustrate the point. There's 2 lines I want to point out. But the other thing you can do in Cython is that you can release the global interpreter lock, or the sort of attached thread state, if you want to think about it like that. So in this case, I've used the C++ standard library as a useful tool because it has things like sets and that kind of thing. And I've released the global interpreter lock. That's just on the middle column, that with no GIL releases the global interpreter lock, so multiple threads can work at once and Python's not getting in the way. And then on the right-hand side, return out. And this generates an implicit conversion back from your C++ set to a Python set, which is kind of what these implicit conversions kind of kill you in this use C++ approach. So what you find at the end of that is that it doesn't actually perform any better on the free threading build than the Python code, like the naive Python code I wrote, but it does take a whole screen. So it's not a big win, but on the regular non-free threading build, you do actually get some benefit of running it in parallel. So if you want to support your non-free threading build, then this kind of thing that you've been able to do for a long time, where you release a global interpreter lock, is the way to go. Just think about how you get the data in and out of Python, as it were. The next thing I wanted to discuss, not so much for creating threads, but for communication within threads, is using the C or C++ standard library. And so my argument here is that if you want things like the mutexes in the threading module require interaction with Python, they are just Python calls. And so if you want these low-level primitives, then then just get them from the C or C++ standard library. Be slightly careful mixing locks and the global interpreter lock, because you can end up deadlocked there. And in the forthcoming version of Cython, so when I say Cython 3.2, it doesn't exist yet, but you can check out the master branch, and most of these things are there. We've written some PySafe versions which avoid these deadlocks with the global interpreter lock. And my general advice is use C++ rather than C, because compiler support is a lot better mainly, and because it's got more stuff. But make your own judgment on that. So, I mean, just as a quick table of things that you've got. You can create threads. You've got atomic numerics. You've got mutexes of different sort. You've got shared mutexes. So that's a read-write lock. So multiple threads can read safely, but only one thread can write safely. You've got condition variables, call once, which does what it says, and sort of semaphores, latches, barriers, which are lower level but faster tools, and a few other things. So you've got all these things which are mostly wrapped in the current release of Cython. One or two will be in the next release. And these are available to you, and you can check them out. And if you want to write sort of fast code, then this is potentially the way to go instead of using the threading module. The most useful of these is C++ atomics. So in this case, I don't really intend to discuss the example at length, but the more interesting stuff's on the right-hand side. So you can do counter fetch add, that's adding 1 to the counter without checking it. And then so what this code does is it kind of increments the counter to 100, and then it resets it to 0, and there's a shared counter between the threads. It's all a bit pointless because the result isn't terribly useful, but it just goes round a few times and does this. But and then the other thing you've got is this compare exchange, and compare exchange is saying if the value equals something that you expect, then put a new value in. Otherwise, go around the loop again. So, I mean, C++ atomics are probably the most useful thing you can take from the C++ standard library. The other thing I wanted to show you is this PySafe feature, which we've added to a few things. So in this case, I'm doing call once. So call once is a sort of a flag which you use to ensure that something only gets called once, kind of as it says. So that's often used for lazy initialization. You want to make sure that you only do your lazy initialization once. So in this case, I've got a function which just prints something. I create a bunch of Python threads at the bottom of the screen that call the function, and it will only end up printed once. And what the PySafe version does is it makes sure that none of the locking can ever deadlock with the global interpreter lock, which is nice. It releases the global interpreter lock if it has to wait. The other thing it does nicely in this case is that you can actually pass it to Python callable. So I've sort of added a bit of an extra wrapper, so you can pass it to Python callable, which will be called with the attached thread state. The C++ version that it's wrapping takes a C++ callable. So yeah, this makes it a little easier to use from Python. This will only be in the next version, I'm afraid. So you can't use it right now unless you want to check out the master branch. The limitations for the C and C++ standard library are compiler support mostly. So MSVC doesn't believe in the C standard library, I'm afraid, or any of the good bits. So if you're on Windows, then that's mainly why I say use C++. But I've also found that macOS isn't astonishingly up to date with the C++ standard library. It's not terrible, but it's not always the most up to date. So if you want a really new feature that's just in C and C++, then you may be limited there. Some of the things, our code generation doesn't work particularly nicely with, mostly things that can't be assigned to, and it can't be default constructed, so semaphore and latch cause problems there, and callbacks are a bit inelegant because Python callables aren't C++ callables. The next thing I want to tell you about is isolated interpreters. So there's been this sort of, in addition to the free threading, there's been this move to make multiple interpreters more useful. So having one interpreter, so having many interpreters in a single Python process. This, from a Cython point of view, this is something of a work in progress. So if you're thinking of putting this in production, please don't. But if you're curious and want to play with it, it's in the state where you can start doing that. So there's a few known bugs and limitations. The main thing is that requiring the global interpreter lock sort of from an arbitrary function may never work because you've kind of got to know what interpreter you're requiring it from. And it needs a recent Python, especially for standard library support. In Cython, it's fairly similar. You've got a subinterpreters compatible directive which says what you want to be compatible with. You compile with this macro, with this C macro. And in Python, really to use it, you want the forthcoming Python 3.14 because it contains in the standard library, possibly controversially named, but in the standard library, the features that you want to access. So just to illustrate the point, the Python side of it is this. So you import the module from the standard library, you create a bunch of interpreters, you can set up queues. There is a backport which gets you to Python 3.12, but my impression is it's buggy, and the idea of the per interpreter global interpreter lock, which lets things run well in parallel, is from Python 3.12 as well. So that's kind of the limit of your useful support. You can put things in the queue. The limitations to what you can put in the queue are, it basically has to be pick a level, a memory view, or a queue. So you're quite limited in what you can put in these queues to communicate between your sub-interpreters. And that's the sort of limit. You call interpreter call in thread, and again, you're limited in what you can pass into it. So my way of thinking of this sub-interpreters is that it's basically multi-processing, but not as painfully slow. So there's a quick benchmark I did with this toy example, which is on the next slide, but multi-processing takes like 7 seconds to do it, and sub-interpreters takes 0.1 seconds. So you've got many of the same limitations. You've got the benefit that they are very isolated from each other, which is both like a curse and a benefit, because you can't easily talk between interpreters, but that stops you from doing stupid things. And then from the Cython side of it, so all I'm doing here is I've got a silly like multiply by 2 conversion. So I read things from the input queue, put things on the output queue when I've done the conversion. So again, it's a trivial example, and this sort of sub-interpreter just keeps going until the queue's exhausted. There's a minor bug in the documentation where QEmpty error doesn't exist. I filed a bug. I'm hoping someone will fix it before 3.14. So I couldn't actually figure out what to catch because the documentation's a web of lies. But hopefully that will be fixed before release. The other thing is your only synchronization primitive is queue. So you can abuse a queue, it's like a single element queue. You can abuse to use the mutex, or you can abuse a queue to look like an event. But this is all you've got to talk between threads, queue or nothing, basically. I don't particularly aim to go into the detail, but you do find yourself coming up with clever misuses of queue, which will make people reading it cry. So, okay, the sort of next bit I want to go through is what's new in Cython. And so I guess the good news is the status of free threading support from Cython 3.1, which is the latest major release. It basically works. You need to declare with this directive Cython 3 threading compatible equals true, and that just sets a flag on your module which says it's compatible. It does nothing else. So this is you promising the Python interpreter. Thank you. This is you promising the Python interpreter that you've got it right. Python thread operations should be mostly thread safe. Non-Python operations is up to you, but but the internal state aims to be thread safe. We don't aim to mess up because you're doing things. The performance is, this is running a bunch of benchmarks we've got. The performance is a little worse, so it's about, I'm going to say about 25% slowdown we're finding. None of these benchmarks are particularly relevant to parallelizing, but yeah, don't expect the performance to be quite as good. So we then present you with some tools that you can use. So the first one is this Cython PyMutex. This is a direct wrapper of the PyMutex type, which is in recent Python. Where the PyMutex type doesn't exist, it falls back to a cruder, older type, which is a bit slower because it needs heap allocation. But the main value of this is a mutex you can use that won't deadlock with the global interpreter lock. It isn't a fair mutex, so in certain pathological conditions you can end up sort of never getting to it, but very few mutexes are, so maybe that's not a huge concern. And this just acts as you put it in a with statement. So you can define it globally. You know, I've got this on the left-hand side, you've got a global PyMutex M, and I put with M, and that's locked the mutex, and it will unlock it, and everything's taken care of it for you. So you're not having to worry about exceptions or anything like that. It can be a member of a CDEF class, so it can be a member of a sort of special compiled class type, and sort of same thing. Or it can be a sort of function local, shared in an inner function, and you can pass it around as a pointer. So you can do lots of things with a PyMutex. It's usable only from Cython, I'm afraid. So if you've got Python code, it can't get to this PyMutex. This is our sort of fallback wrapper. It's mainly used for the limited API, so I don't think I should say a lot about it. But equally, we've ensured for your benefit that there's no deadlock with the global interpreter lock. The second thing we provide is Cython critical section. So critical section is something that's built into Python as a tool they use to make things work. It's kind of a mini per object global interpreter lock, and it's a no-op on regular Python builds. So, I mean, this in the same way is also a context manager. You say with Cython critical section, and then you just put it on any Python object. You can use it as a decorator, and it gets applied to the self argument. And you can use it as a 2-argument version. So, yeah, it's reasonably straightforward to use. Unlike PyMutex, critical section can be interrupted, and this is kind of the difference, that a critical section, it won't deadlock, but it can be interrupted by other nested critical sections. So you can nest them how you like, which you can't do with mutexes. But yeah, it doesn't a whole critical section doesn't guarantee to be run in sort of one go, and that's both a strength and a weakness. And the main thing that breaks it is Python attribute lookup. So if you do anything that's looking up a Python object, that you essentially uses getAttra, then it will break your critical sections. So my advice is using it to guard sort of CDEF attributes on CDEF classes where you don't have Python attribute lookup. So this is just an example, this sort of lazily initialized. So here you're saying you've got a with Cython critical section. If the value you want to lazily initialize is none, then you initialize it. And the point is that the make lazy object may interrupt the critical section. But often that's okay. You don't really care if it gets initialized twice. You just want things not to be corrupt. And then again, sort of think about what types you're using. So critical sections, like in principle, a cint will be consistent inside a critical section. A Python int probably should be. Fraction appears to be, but I don't see why. And this surprised me. I couldn't make this test break. But certainly with the global interpreter lock on a non-free threading build, fraction may be inconsistent if you're running it from multiple threads. And there's a bunch of places where it can be interrupted. You've got allocations, you've potentially got a destructor involved in that. So think about that. The general approach we're taking is that thank you, is that Python operations should be safe. So things like list indexing, you should be safe to do. Things like accessing module globals in dictionaries. C operations aren't safe, so that includes cdef variables, and so they're your responsibility to add locking if you want it to work. And inaccessible internals, things like we've got a code object cache, that kind of thing, dispatch perfuse functions. You know, I've been going through and fixing them, and they are now mostly safe. So, I mean, this is just a kind of quick tick box thing. So module globals, cdef module globals aren't thread safe, but other module globals are. I may change that because I think that's probably I think for the next version I may end up changing that, just because I think we'll regret it. Things like generators are safe because they've got a running check. Attributes of cdef classes aren't safe by default. Locals, if they're not in a p-range function, they're kind of safe by definition, but because no other thread can access them. But so this is kind of the current status. We may change or improve some of this, but this is kind of a guide to what you need to guard. You know, if you've got variables in the cdef class, you need to be adding guards. And then I think this is kind of heading to the end of what I want to say, but a quick sort of guide to making your mod. So if you've got a Cython module and you want to make it thread safe, you first, I'll go and identify in the global state you've got like lazily constructed globals is something that a lot of people have, and you know, put guards around them. That you'll regret. If you've got any restrictions, document them. So if you want to say this X class can only be used for one thread, which is a reasonable thing to do, put it in the documentation. If you want to say, don't mess around with lists that you're passing to my function while my function processes it, put that in the documentation. It's a reasonable thing to say. You know, don't try to cover everything. Add the free threading compatible directive to tell it that it should work in the free threading interpreter. Add tests. There's this PyTest run parallel feature. And the sort of final point is probably already broken anyway. So much of the bugs you have in free threading actually happen if you're using parallelism not in free threading. So from that point of view, you're probably not making it worse. So to an extent, my advice is kind of get on with it and see if bugs get reported rather than wait to make it perfect. That is genuinely my last slide. So hopefully you've learned something.
All right, thank you so much for the presentation. Are there any questions? If yes, you can feel free to come to the mic and ask. But if you're still thinking, I do have one question for you, because you gave a lot of advice throughout and maybe some, fun facts throughout your presentation. And I want to ask you a question about your advice on what resources should be recommended for developers that want to start the journey with, for example, diving deeper with thread safety and exploring that topic?
So I guess I don't really know the top level resources, so I'm probably a bad person to ask about that. Mm-hmm. In terms of Cython, we've written some guidance for the subject. I've been sort of writing this in preparation, which unfortunately, if you've read the guidance already, spoiled most of the talk. I know Quansight have been producing a bunch of guidance, the general problem for extension module authors, covering a lot of this stuff, but not just Cython, more generally. So if you're an extension module author, then the Quansight documentation, which they've linked fairly prominently, but I can't remember the address off the top of my head. But yeah, I'm not sure if you want to get started completely from scratch and learn about these things, I'm not sure where I'd go as a first reference, I'm afraid.
All right. Still, thank you so much. Are there any questions? Okay, then. Oh, yes. Do you want? I'm going to give you a mic.
Thank you. So yesterday we had a session on speeding up scientific code with JAX and advantages of vectorization. So when would you recommend using Cython and when would you recommend vectorization?
When vectorization doesn't work, so not everything is vectorizable. Things where things where you've got a loop, if you've got a loop and each value is independent, then that's vectorizable. Use vectorization, it's great. If each value depends on the previous one, then vectorization just fails. You know, the assumptions it's based on don't hold. And in that case, Cython can be really good because it makes the loop actually run at a decent speed, you know, and finish in time. So that's kind of my advice. I honestly recommend, you know, if NumPy does what you want, it's very good, very fast. Use NumPy.
Right.
We fill the gaps where NumPy begins to fail.
Makes sense, yeah, thanks.
All right, since I don't think I see any more questions, once again, thank you so much for your presentation.
Thank you all for coming.